everyone, my name is Jillian Bradley. I use she, her pronouns, and I'm a third-year chemistry graduate student in the Wasilewski group here at Northwestern University. Originally, I'm from Mansfield, Texas, and for anyone who's never heard of Mansfield, it's pretty close to Dallas. When I'm not doing research, I enjoy spending time with my horse Tug, volunteering at a nearby cat sanctuary, playing video games, mostly esports titles these days, and during quarantine I've even started doing some drawing and sculpting again. For my research, I investigate charge transfer in organic molecules. So in modern society, we are pretty familiar with the idea of electrons moving from one place to another through a metal wire. It is the basis for all of our electrical devices after all. And it turns out that electrons can move through some organic molecules too. This is usually true for molecules that are highly conjugated. A conjugated molecule has several double bonds sequenced together, with one single bond in between each of the double bonds. These kinds of structures are good at stabilizing charges, at least for a little while, and this is important to allow for electron mobility. For example, this is a molecule called perixanthinoxanthine, or PXX, that I often work with in my research. And for anybody who is not familiar with skeletal structure drawings for organic molecules, each unlabeled vertex would be a carbon atom. Hydrogen atoms that are bonded to carbons also get omitted, and so if it looks like a carbon atom has too few bonds to satisfy the octet rule, that means all of the quote-unquote missing bonds are to hydrogen atoms. The main thing that I study in my research is light-driven charge transfer between organic molecules. This process has some important applications in devices like solar cells, which use energy from photons to generate an electric current. For my research, I synthesize molecules that have a charge donor and a charge acceptor, and of course they are also able to absorb light. Shining light on these molecules causes an electron in the donor to become excited, meaning it has a lot of energy. And because it has so much energy, this allows the charge to move from the donor to the acceptor, thus creating a charge transfer state. But since the charge transfer state is not as stable as the neutral or ground state, the charge then tends to move back to the donor after a little while. Also, I can measure how long the charge-separated state lives by using a technique called transient absorption, or TA, spectroscopy. And spectroscopy is a fancy word for experiments that measure a material's response when it gets exposed to light. In my lab, and in a lot of labs at Northwestern, we have instruments that can record which wavelengths of light a molecule absorbs. The dataset we get, called an absorbance spectrum, looks kind of like a line graph. It looks kind of like this. And it's unique to each molecule. What TA spectroscopy does is stimulate the molecule with a laser pulse. Yes, we do use lasers, it's very exciting. And then the experiment measures a bunch of absorbance spectra over time, and we get a data set that looks kind of like this. Putting a charge on the molecule causes its absorbance spectrum to change, so we can use this method to track how long it takes for the charge transfer state to form and how long it lives before the ground state gets regenerated. In my research, I have to consider the oxidation and reduction potentials of my charge donors and acceptors. This is because after my molecules absorb light, they undergo an intramolecular redox reaction. For example, in this molecule that I made, the overall reaction would be that the donor, PXX, absorbs a photon, gets excited, and transfers an electron to the acceptor, naphthalene diimide, or NDI. However, redox reactions are composed of several smaller half reactions. In this case, my oxidation half reaction is that PXX forms the PXX radical cation and a free electron. This takes 0.8 volts of energy. All of the potential energies I'm going to list are in volts versus SCE. Negative potential means that you have to put that amount of energy in for the reaction to happen, while a positive potential means that the reaction will happen spontaneously and release that amount of energy when it occurs. So oxidizing PXX takes 0.8 volts of energy, while reducing NDI takes 0.5 volts of energy. However, the electron also has to pass through the bridge, naphthalene monoimide, or NMI, before it can get to the NDI. So I also need to know the reduction potential of NMI, which is negative 1.3 volts. In total, transferring the electron from PXX to NMI would take 0.8 plus 1.3 equals 2.1 volts of energy. When PXX absorbs a photon, the excited electron gains 2.9 volts of energy. And so this gives 0.8 volts of driving force for the first charge transfer. After that, transferring the electron from NMI releases 1.3 volts of energy, while reducing NDI only takes 0.8 volts. So the second electron transfer will happen spontaneously, no more light needed to drive it. And since I don't want to spend a bunch of time making molecules that can't undergo this light-driven charge transfer, it's really important to do this math beforehand to make sure that the process is feasible. In my future research, I can replace NDI with titanium dioxide, or TiO2, since they have nearly the same reduction potential and TiO2 makes a really good anode. Then I can connect the photoanode to a cathode with a wire. And then the really exciting part is that I can also attach a catalyst to the anode for something like water splitting, which is a really desirable reaction to make hydrogen fuel. From your lectures, you may remember electrolytic cells. Unlike a galvanic cell, which utilizes a spontaneous electrochemical reaction to make an electric current, an electrolytic cell requires an electric current from an outside source, such as a battery, to drive a non-spontaneous reaction. Well, this setup would make a sort of electrolytic cell, only instead of requiring an electric current from a battery, it gets all the energy it needs from light. And ideally, the cell could use that light energy to help drive important catalytic reactions, like the production of hydrogen fuel from water. I have always wanted to do research, mostly because I'm a huge nerd and I really enjoy learning new things. So a career in research always seemed like a dream come true for me. So in my sophomore year, I jumped at the chance to join a summer research program with my undergraduate institution, and that's something I would definitely recommend for anybody considering a career in science. During that time, I worked on organic synthesis, and it was really exciting to make new molecules. So I set my sights on graduate school, and a few years later, here I am at Northwestern, still doing research and still living that nerdy scientist dream.